Good morning, everybody, and thanks for joining our data search research talk series. We have an exciting researcher to present today, Dr. Sachi. Sachi is a proud alumni of University of Moratuwa. He has completed his undergraduate degree here and a gold medalist. He's a colleague of mine since then. And then he has obtained his PhD in MIT, I believe, right? And then worked for Google for his on self-driving cars, and continue to work on autonomous vehicles, right? That's his area, primary area, and have been an active researcher and a hands-on practitioner in this area, and agreed to help us by delivering this talk. Very nice of him to share his hour with us all the way from USA. Appreciate it, Dr. Sachi, and thanks for your time. Over to you.
Let me present. Okay, awesome. Hope you guys can hear me.
We can see. You can see.
Okay, cool. Sounds good. Okay, cool. So hopefully this talk is informative and useful to people. So today I'm going to be talking about some details about how we can go solve real problems with machine learning and AI. I think from what I understand, most of you guys are studying machine learning, so feels like a good topic to discuss. So let me give you a quick introduction about me. I'm a student of University of Moratuwa. I did my bachelor's in electronics and telecommunication. Within that time, I studied electronics, telecom, but did some robotics related things as well. So, and after that, after a while, I went to do my PhD and master's and at MIT, and I specialized in robotics. Within that field, I worked on semantic mapping, so mapping that contains high-level information about the environment. So, and how we can use natural language understanding to interact with robots. It's actually a picture of my PhD robot. So this is a assistive wheelchair setup that we were using to both interact with people in the environment, also navigate and carry out different tasks. So within this time, I worked on perception and planning related to robotic applications. And after my PhD, I have been working in robotics and self-driving. I started out at Google Robotics, where I worked in indoor robotics. And for about 8 years, I've been working in self-driving, first at Google, then at Toyota, and now at Cruise. And within this, I've worked in object perception and tracking. So this deals mostly with using sensor data to understand the environment and understanding the state of the world. So how fast objects are moving, what type of objects they are, things like that. And this has touched on both machine learning as well as more traditional algorithmic approaches. So that's a quick highlight to give you guys some context. So I was hoping to touch through a few things, kind of give an overview of AI evolution in the last 50, 60 years, and maybe talk a little bit about applications of artificial intelligence and machine learning, and specifically deep dive a little bit into like robotics and vision related applications. And then maybe something also more forward looking for you guys is kind of how is machine learning and AI used in the real world. So I think typically in academia, there's some applications or approaches to machine learning, whereas sometimes in industry, it tends to be focused on different things, and maybe go through a little bit of the machine learning life cycle. And then hopefully we can have some time for questions and discussions. Okay, cool. So machine learning, I think it's a little bit of a loaded term, especially AI. So I think AI started out in maybe like 1950s, 60s as initially kind of this rule-based symbolic AI. So uh, people looked at how humans reasoned about the world and wanted to build computer systems that can kind of approximate them. So the first approach that people did were come up with like these explicit mappings of what we think of as intelligence and try to map them into computer representations. Unfortunately, this didn't really work out too well. So in the 60s, 70s, the hype kind of died down. But after that, more simpler techniques developed to actually do solve more useful day-to-day problems rather than solving like general intelligence or trying to make a human-like computer. So kind of like the second wave of machine learning and AI was more like simpler techniques, people taking data and kind of tuning it to solve a problem. Unfortunately, in the earlier days, there was not too much data related to some of these problems. For example, computer vision didn't have a lot of data sets. Computers were very limited. It didn't have the capability to really solve these problems at the scale that it needed to be solved to gain the human-like performances that we see now. And but more in the late like 2010s, sometime in the early 2000s to 2010 time period, there was a big revolution in both the scale of data available as well as the compute resources available. And this, in addition to some of these new techniques like backpropagation and deep neural networks that were around a while ago, but really didn't have the right resources to actually make use of, they actually started providing benefits. And within that time, major advances were made in machine learning and computer vision. And this is kind of like the start of the big machine learning and AI revolution that you're seeing these days. And more recently, I guess AI has been in the news in terms of this generative AI, ChatGPT, the techniques called transformers that kind of started off some of these revolutions, and some of these larger models and much large scale data sets than even what we were used to 10 years ago. They've significantly unlocked the capabilities of these machine learning systems to the level that uh, people are kind of surprised or can't even tell the difference between a human and a robot in some cases. This was kind of an old test from what's called Turing test in the old days that is not really used more recently, but it's kind of can a human be fooled by a computer to the level that human can't tell whether it's a human or a computer that they're talking to. So at this point, I think in some of these generative models, you approach the state where a human can easily be fooled to think that it's not a computer, but a human being that's on the other end. So this is kind of some of the high level steps that we've gone through. I think the future is unknown. I think one remaining frontier that people are working towards is kind of this general artificial intelligence. I guess if you listen to Elon Musk or someone, there's a lot of talk about general AI, and that's kind of like human level AI, where it's not like a very specialized task that you're trying to solve, but kind of building a system that can understand and do most things that we think of as intelligent. A lot of the systems that we see today, they are very, or to a level, very focused on certain applications. What just mind, Deep Blue, I think, the one that played chess and beat humans. They are very targeted at certain applications. Even now, a lot of these neural networks that are built that are very capable and beating humans, they are very targeted at certain domains. If you take that and ask it to bring you your coffee, there's no way for it to even understand what you're talking about in a lot of cases. Um, so I would group AI as like in industry, especially as kind of three high level groupings. There's a lot of these broad application cases where they're not like very critical applications where safety is not a key thing, like a Google search, for example. Of course, like 99.99% of the time you want to get the answer right, but there's no like safety critical failure if your answer is sometimes wrong. So there's a lot of broad applications like this, and there's a lot of use cases where AI is very immediately applicable. So in these cases, most of the time, it's average performance that matters. So a lot of these standard metrics that you see in machine learning, they're very applicable to these kinds of applications. And whatever you get as the output to the model, a lot of times you might be able to directly use that output. The human can decide to consume it or may be able to verify it while they're using it in a non-critical manner. Then there are other cases where like you have critical applications, but the machine learning system is able to really give something insightful, but it doesn't have to be perfect because there's a human in the loop. So they may not be like latency critical applications. You can think of like health diagnosis where the machine learning model is still very good, very performant on giving some good hypothesis, but it's never making the decision to really treat the patient. It might suggest some things and the doctor will look at it and decide actually what to do or further diagnose the situation before it takes action. But in these cases, the human makes the last call. So getting it right is required, but not critical to the level that you would think. So the bar is still not super, super high, I would say. And then there are critical applications where the machine learning system or robot or whatever this case might be needs to make a decision without a human involvement. Either maybe imagine like you have a rover on Mars that needs to actually pan the path and maybe not hit a rock. There's too much latency for it to decide something, ask a human, and actually then take the action in most cases. So in that case, autonomy and the system being able to decide is critical. Similarly, for something like self-driving cars, you need to let the system actually take action or at least decide in a safe manner that it doesn't know what it's supposed to do and safely force and request a human support. So these are like the critical of applications that can be limited, but there's large payoffs if machine learning or approaches can really solve these kinds of applications. But these kinds of applications require a lot of validation and high bar to actually use machine learning safely. And so if you think about it, there's a lot of strengths in AI, like especially the type of machine learning and artificial intelligence that we have right now. A lot of it is actually learned from data, whereas maybe 10 years ago or 20 years ago, there are a lot of human engineering underpinning these techniques. Like you might do a lot of human engineering to supervise features, which means that a lot of expert knowledge that actually goes into making those systems work. More and more what we see now is that, especially with these deep learning techniques, the features are learned from data as opposed to someone engineering how to detect an edge corner or like a corner or an edge of an image such that it can then better classify if it's a car or a bicycle. And what this means that it's more about getting the data and the right type of data and supervising these models end to end as opposed to having heavy engineering efforts to maintain and improve these systems. And as we've started getting more big data, like massive data sets, and you have a lot of public data now with computer vision data, robotics and self-driving data, these models are able to learn much more effectively. And in the last 10, 20 years, there have been major advances in a lot of these architectures that we use now for solving computer vision or natural language. And combining these two with the kind of computation that we have right now, these models are able to perform or even in some cases outperform humans in specialized tasks. It may sometimes struggle in like corner cases where a human with the human level of intelligence can generalize better from seeing two types of specific examples. It can really, people can understand, oh, I just need to do this because I knew exactly what I did last time. But these models can't generalize to that level, but in general, they're able to really solve these problems to the level of humans. And the faster GPUs and a lot of these parallel computing and techniques that people have been developing more recently, they are continuing to accelerate how much we can train and how fast we can train these models and experiment with these models. But machine learning comes with a set of weaknesses, at least right now. like I was saying, unlike humans, a lot of these models, at least what we have right now, they don't generalize. And sometimes you can get to situations where these models may not have seen the type of data in its training, and then they will do something unpredictable. So especially when it comes to safety critical applications, ensuring you have good coverage, making sure that your models are well tested in the kind of critical slices that you care about, it matters. Otherwise, you cannot safely deploy these systems to solve critical applications. And in a lot of machine learning cases, like imagine computer vision, where you're trying to classify and recognize thousands of types of objects, there would be like 80% of these examples would be coming from 20% of the types of classes that you want. And there's a lot of rare examples. But when you're trying to use it, depending on the application, you want it to perform well for all of these applications. Like a human might recognize a very rare animal once the person's seen that example a couple of times, but these models don't work to that same level. So it has challenges working as well on rare examples. And when they're unpredictable or hard to interpret, sometimes they can't be adopted as easily in some of these safety critical applications, or if there is a failure, there's a problem of understanding what actually led to the failure, whether it's data, whether it's training, whether it's something else. So these are kind of the current challenges of machine learning, especially when it comes to certain industries. But on the good side, there's a lot of state-of-the-art applications of AI in the current industry. So you can think of like information retrieval, like Google search or ChatGPT. There's a lot of machine learning techniques applied to find the right answer or generate the right response. A lot of healthcare and diagnosis, machine learning is making its way, doing better diagnosis, or at least providing the options that doctors can use to find the right diagnosis or medicine that they should be using. A lot of these new things like generative text or diffusion models creating art that is, or images that are very human-like in terms of like quality and um, relevance to what we want. They are kind of revolutionizing a lot of these creative space in some sense. There's lots of protests and other things going on right now in like Hollywood because people are afraid that AI will like remove the need for human actors because these systems can generate like a Tom Cruise like image in the movie without actually needing the actual person to be there. Some other exciting kind of applications that are now coming to pass due to machine learning is in robotics and self-driving. I will deep dive a little bit into some of those applications. Finance and automated trading, AI assistants like Google Assistant, Siri, and more recently some of these games like AlphaGo, where these supervised learning or reinforcement learning kind of approaches have led to very complicated games that maybe 5-10 years ago, people didn't really see that AI could really solve it because of the complexity involved. These problems have been solved in the last 5-10 years. So ML has made significant progress, and as it's making progress, it's entering a lot of industries to the level that it's changing how much humans may be contributing to some of these industries in another 10 years or 20 years in time. And one set of advances have been coming in terms of computer vision and AI, like I would say 2 types of machine learning that people have been working on for a lot of time is understanding natural language and computer vision, because these are kind of the critical things that people use to understand the world. And so these have been kind of the top challenging applications that people have been working for decades. And object recognition and detection tasks have been like standard machine learning challenges that people have been using for decades. And especially in the last 10-20 years, a lot of these like convolution networks, deep architectures using neural networks, they've really started to push the boundary of performance to the level that we're now able to like match or even beat performance of humans in a lot of these examples. And these kinds of advancements have actually led to the next step of what I'm going to talk about, and that's machine learning in robotics. So robotics has a lot of applications. Right now, they're in the early phase where the impact of robotics in a lot of these industries is still early on. But as they become more and more capable, they will start to scale out the impact of these systems much more widely. And a lot of these technologies require machine learning to really robustly perform what they're doing right now. And robotics kind of has three pieces. You kind of sense your environment, you predict how the environment will change, and then you act based on it, based on some goal that maybe it's encoded in the robot itself, or a human might be providing this robot. And a lot of robotics started out in assembly, especially in like automotive assembly. A lot of images and videos of robots that people think of tend to be these giant robots in factory floors, building a whole bunch of complicated pieces together to build a car with lots of sparks flying and things like that. But more and more robots are entering human spaces, whether it's home robotics, self-driving vehicles on the road, delivery vehicles or drones, agricultural robots, even factory floors. There are now much more push to make robots work with humans instead of in a very separated environment. In the past, and even now in a lot of industrial setups, you have robots cordoned off into some big spaces. Humans cannot go into those spaces without like ensuring that those robots are turned off. But more and more, as these systems become more aware of the environment and able to interact with humans, the collaborative aspect of humans and robots in these spaces is becoming more and more pronounced. So in the picture, you can see a bunch of applications of robots. Some of these are in earlier phases, some of these are actively developing in industry, but they're all applications that are becoming more robust and generalizable because of machine learning. In the old days, people would hard code some thresholds and configurations and kind of make it work in one application. One house or one factory to understand the robotic systems can generalize across multiple domains or multiple different environments. So going a little bit deep into robotics, hopefully this is interesting to you guys. It's a bit of a special application of machine learning. Typically, like Google search or some ChatGPT or some generative AI, they're more passive kind of applications. You ask it a question, it provides you an answer, but it doesn't really change the immediate environment very directly. Whereas in robotics, a lot of times there's a quick loop about you perceive the environment, you understand how the environment is changing, you may have a goal and you try to act on it. And by doing that action, you change the next step. In the next time iteration, what you're sensing is kind of sometimes a direct response to what you did in the last time. So in these cases, a lot of robotic applications, response times matters. You need to be able to figure out what you're sensing and predicting in a matter of 10 to 100 milliseconds in fast moving environments like self-driving. And depending on the type of application, if one of these pieces, or sometimes the whole thing, if it's like end-to-end learned, if something critical fails, it can lead to a safety critical failure. So taking, for example, a self-driving car or a robotic system, you may start out with a set of sensors. You might have cameras, you have lidars, you have radars, and within each timestamp, you run a task called detection. In each of these sensors or together, you're trying to detect what is around the vehicle or the robot in this environment. And based on that, you track these objects across time. So you might be getting these observations from cameras, lidars. You want to understand continuously, oh, I'm seeing one car moving, there's a pedestrian moving, the car is moving at 20 miles an hour, things like that. And then you also want to understand some of these high level information about the agents in the environment. So what does this look like? If you take self-driving cars, for example, on the left picture, you guys can see what I'm showing. Okay. On the left picture, you're seeing an image of LiDAR or a point cloud. This is like a typical sensor that self-driving vehicles or robots use to perceive the environment. It shoots a laser beam at very high rate out to the world in a moving, like spinning setup, and it's getting these returns back. So it knows how far away each object is in very high frequency, like 10 hertz or something. You may have cameras observing the environment. You can see pedestrians, cyclists, vehicles around. And at each time step, these machine learning algorithms are used to detect these objects, like cohesive objects like vehicles or pedestrians, in cameras, in LiDARs, in radar. And then at each time step, you're taking this and you're understanding the previous across time, this is the same object. And based on the fact that I saw it moving from one point to another point to another point, you want to estimate its velocity, its shape, its type, things like that. And in addition, you also want to understand, okay, is that a person? Is that person gesturing to me? Is that person holding a sign? Is that a vehicle? Is it like an emergency vehicle? Is it having flashing lights, things like that? And all this information is needed to actually better predict what the world will evolve based on your actions. So the next step is called prediction. And prediction is basically taking the information that you are seeing about the environment and some additional information like a map or known rules about how agents interact to predict across multiple seconds into the future, how would they behave? And sometimes how would they behave based on what you may do? Like if I go forward, what would the behavior be versus if I stop, what would the behavior be? And a lot of times this is mostly learned from machine learning using data based on observing a lot of agents in the environment that you're collecting. Let me take an example. You have a vehicle, let's say at time zero, you observed it moving at 20 miles an hour and it's approaching an intersection. If you naively assume that it will continue to move 20 miles an hour and not reason about the intersection, you may think that, oh, it's gonna cut in front of me and it might collide, so I need to stop. But in reality, let's say you also know that the traffic light is red for that vehicle, in which case now you're predicting it into the future to understand what should I do, similar to how a human would behave at an intersection. So at that point, based on all this information, the model is able to produce that the vehicle will most likely come to a stop. It may not come to a stop. So as time evolves, you might decide differently, but for the moment, the most likely prediction is that it will come to a stop. And typically, a robot or self-driving vehicle will be doing this kind of prediction for a lot of these objects around the world, around itself. And based on that, it will plan and act on this information and what it's trying to do. So let's say you have a car, it needs to go to some specific location, and it knows where it is, it knows what's around it knows how these agents around it will behave, and based on that, it will compute and execute some path, like a set of positions and velocities that it wants to do to get to that goal. So imagine a vehicle driving to a location, robot being asked to pick up a cup, or some robot tests, or like some AI agent that's talking to you and discussing and answering questions. And the whole point here is learning what the optimal action is from data, ideally. This is kind of a challenging case because if you want very safety critical behavior, sometimes just machine learning may not work in this kind of case, or at least not robustly work. So you may have safety checks and additional algorithms to ensure that you're behaving safely and within constraints of the system. But in this case, imagine you're the self-driving vehicle or the autonomous vehicle, you have a pedestrian moving in front of you, and you're able to predict its motion across some number of seconds. And based on this, it's going to decide, okay, if I slow down and go around the pedestrian, this is the best action. based on the fact of like, oh, I don't want to risk hitting the pedestrian. I don't want to suddenly jerk and brake if the pedestrian crosses in front of me, things like that. And typically, some or most of these pieces could be learned from data with sufficient amount of examples. But the challenge is that you want to be safe and predictable in all cases, and you may not observe all the kind of interactions that these agents will do for these systems. And the last piece of this robotic puzzle, I would say, is interaction with humans. And in a lot of these systems, maybe not self-driving, but a lot of robotic systems, the end goal is that you want them operating and doing useful things in the human environment, whether it's like an office, your house, in the field, or in a factory. And in that sense, you want these systems to understand and interact with humans. And one easy way is natural language. Like humans are used to talking to humans to explain what they want and figuring out how to solve some problem. Similarly, these robots ideally want to interact and also understand information about the environment relative useful for how they need to achieve their goal. So if I say, robot, go put these dishes in the dishwasher, it's in the kitchen down the hall and on your right, I'm telling the robot both what it needs to do, but also some amount of information about the layout of the world that it needs to understand. And so in order to perform this task, the robot both needs to understand what I was telling, but also kind of map it to entities around the world that may encounter or already knows about. And in this sense, a lot of recent machine learning advances have significantly advanced the performance of these kinds of actions. The perception techniques that I was talking about earlier, with detecting with convolutional networks, things like that, allows very good recognition of types of objects in the environment, or kind of even the broader state of the environment, like is it in a kitchen, is it in a living room, things like that. Natural language, like speech recognition and natural language understanding, have significantly improved with things like transformers and other things. So a lot of these systems' ability to now understand and map to human concepts are at a level that you can actually get these systems to do useful things. They may not be as fast as humans yet. A lot of these manipulation robots, their manipulation arms tend to be very expensive and slow. Sometimes the planning algorithms still take too long, but they're advancing at a rate where in the future, within 5-10 years, they will be at a stage of being able to like go into a new environment, open up a drawer, pick up a bag of chips, for example, and bring it to you and satisfy what you requested from the robot. So hopefully that's a kind of a useful example of how some of these machine learning techniques have influenced these kinds of very cutting edge kinds of use cases. And next, I will move on to kind of machine learning in the industry more broadly, and how machine learning is used in industry versus research, for example. I'm not fully sure how much kind of research work you guys have been doing, but generally there's a broader difference between research and industry. Typically in research, a lot of focus, especially in machine learning, is more on publishing or advancing the state of the art. And this is great. A lot of the time, the focus is on showing improvements on a lot of standard metrics, especially a lot of these mature kind of machine learning domains like computer vision or natural language. There's a big set of standard data sets. There's a set of good benchmarks now with a lot of state-of-the-art algorithms. There's leaderboards. If you kind of go find like a standard data set, there's a good leaderboard of, okay, these are the 5 different top performing techniques. And you care about like good performance on a lot of these, like mean average precision or PR curves, things like that. So a lot of focus is on like new architectures that move the boundary of some of these metrics, or new loss functions that help you converge faster or improve performance, or some sort of new theoretical proof. And this is kind of the pushing the boundary of human knowledge in a lot of sense. and you have a lot of standard data sets. Whereas if you go to industry, a lot of it is about solving business problems or problems that actually need a solution efficiently. So it's not about like the perfect performance or the best PR curve or precision or recall, but it's more about what is sufficient to solve the problem, and in some cases, what is sufficient to solve the long tail or challenging examples, depending on how critical it is. And a lot of times, it's not necessarily about the best state-of-the-art technique that you want to apply. Sometimes it may be behind like 2 years, 5 years, depending whatever. But sometimes some of these earlier architectures are still good enough. It's more the challenge is on finding the right amount of data, finding the good distribution of data to really make these techniques work for the problem that you want to solve. And sometimes, depending on the domain, it's very difficult to collect data or collect data ahead of time before you kind of deploy the system. So that is most of the time you're dealing with data and pipelines as opposed to trying out the best or the greatest machine learning model. And sometimes, a lot of times, even if you have data, it's more a question of how well your labeling is, how high quality your labeling is for the data that you care about. That really means that the model works or not, especially on the use cases that you want. And typically, there's a kind of life cycle within machine learning. Like I said, everything starts with data and kind of ends with data. So you have data or you need to collect data sometimes, and then you start from the next step. Once you have data, you want to model it. You may have your training set up, you model, you pick some approaches that you want to do to solve the problem, and then you want to evaluate it to make sure that it's performing to your specifications. And then let's say you deploy it in whatever application. Let's say it's a robot, it's out there now collecting data, interacting in the environment with this model. But inevitably, some parts of these models will fail in some certain circumstances, and now you want to continuously improve it. And in such cases, you want to mine these kinds of failure examples, add to your data, continue to iterate on your model. So that's kind of the cycle and the loop that you go through typically, especially if a machine learning model or a system is continuously deployed and serving customers and expanding. You're never fully solved in most cases. You still need to improve, you still need to iterate. And most of the time, you may improve with data, you may iterate in the model, you may evaluate and find different failure cases. It's kind of the whole cycle of this setup that you go through. And like I said, in most cases, data is the biggest challenge. And depending on the domain, it can be challenging to obtain data or the type of data that you want. Maybe your model needs to really handle and detect very rare cases of some type of object for like a self-driving car. Maybe you need to find and ensure that you don't run over debris on the road or tires and things like that. Finding such rare examples is very challenging, especially if you want to deploy this model. So sometimes you may have to data mine, you may augment your data with a few examples, but make sure that the model gets sufficiently diverse types of inputs, things like that. And you may try to bootstrap with existing data, especially if you have some publicly available but usable kind of data that's legally viable. You might try to use that to kind of create an initial model, mine data, things like that. And then once you have enough data, you need to label this data, make sure that the quality of these labels is sufficient. And a lot of this is spent on labeling. There's companies that are now like worth billions of dollars that are basically just focused on labeling accurately or labeling at scale and ensuring that the quality of the data is good. Sometimes you have to go through multiple rounds. You may get data labeled. You need to verify that the labeling is sufficient. Then you may need to relabel or ask for these failure cases and kind of ensure that your labeling is better. Then the next step is kind of modeling. A lot of advances have been happening in terms of modeling. There's lots of state-of-the-art modeling frameworks like TensorFlow, PyTorch, things like that. There's ecosystems built around these where a lot of these, especially now with machine learning, some papers come out almost all the time now. model and code is made available, and you have examples of how to run them. So as someone in university student, for example, if they want to try out an application or an example to familiarize yourself, or just try out a model for like some project or something, the code is available. The code is not necessarily the availability of the prior art is not necessarily the big blocker. It's more about figuring out your application and really kind of advancing the state of things. And even in industry, maybe you have access to state-of-the-art architectures, but it's more about how do you find the right architecture that works for the problem that you have. So depending on the application, there may be still constraints. You can't take the biggest model that you have in the lying around and apply it to the problem that you're trying to solve. You need to find the right model that works. So if it's like a robotic system or like some embedded system, you may not be able to use a really high capacity model. Likewise, if you have only a limited amount of data, you can't use a very over capacity model because it will overfit, and then you may get very high confidence performance on your like limited data at testing time, but when you actually run it in training time, it will not work like you expect it to work. So these kinds of things matter, and typically this is the kind of cycle you go through. And especially if you're trying to build a very complicated machine learning system with lots of different kind of data slices and data sets, you may want to go through different steps, similar to how you might do some solving a problem. You might start with a small data set, train a model, simply just let it overfit, build it up, expand the experiment, add more data, scale up the architecture, try out different experiments, and gradually build up the solution, as opposed to trying out 5 different models and throwing a huge amount of data at it and hoping that one of these works. It doesn't necessarily work like that. And as you're modeling and while you're iterating, typically you want to evaluate your model. So evaluation is a key piece of understanding how the model is working, and ensuring that you have a good data split between your training data and testing data is vital. Sometimes if you're not careful, the same object might appear in testing and training, and you might end up thinking that your model is much more performant because it's seeing the data itself when it's being trained. So ensuring those kinds of things is pretty important. And sometimes, depending on the application, you need to find the critical slices that matter for high consequences, and making sure that the model isn't just performing well on easy examples, but on the hard examples, it's still able to really perform well. And sometimes this is what matters to shipping a model or not shipping a model. And sometimes out of domain examples can be especially challenging. It's hard to get those kinds of examples. If you had them, they would not necessarily be out of domain, but ensuring that generalizability and things like that with evaluation is a big piece of deploying these systems, especially if they're safety critical systems. And like I said, once this model is deployed, you want to continuously improve it. So you want to find examples in the real world and continue to update your model with data. You might want to mine data where the model is right now performing poorly, and continue to add this data, but make the model perform better on everything. Okay, so this is kind of what typical machine learning industry is like, especially if you're dealing with shipping models to some of these safety critical systems. That's kind of the life cycle of things. So I want to conclude, I think, like I said, machine learning is like becoming very performant, especially performant to the level of meeting or beating humans in certain domains. And it's now making its way into a lot of domains. So it has a lot of potential, and anyone working in machine learning is pretty high demand right now. It does have some limitations, and sometimes machine learning in the public has a lot of hype, and sometimes the hype is warranted, sometimes it's not necessarily warranted to the level that it is. But as someone who's working in machine learning, it's important to kind of know what it's capable of, know what the limitations are, and how to best apply it in solving real world applications. So I think that's the kind of skills you want to build up as you work on research or go to the real world. And sometimes in research, it's more about pushing the boundary. In industry, it's about solving the problem, and sometimes solving the problem robustly. So hopefully that's the idea that I would like to convey to people. Anyway, I think we have some time. I'm happy to answer any questions, or if you guys have anything else to ask.
Thank you, Dr. Sachithra, for the nice talk. I will be moderating the Q&A session. But in the meantime, I would like to ask you, so as a person who has been working in self-driving cars for a long time, what changed during the last 3-4 years in the area of self-driving research or industry? What's the latest?
So I think when I started out originally in self-driving, there's a lot more like algorithms and heuristic approaches to systems, but then more and more of these advances were coming into the public view. So a lot of these deep neural networks, these REST nets, things like that, and transformers, they were making its way into the domain, and then people started using more and more machine learning, and especially with a lot of these bigger companies started getting more data as well. So those two, coupled with a lot of these ongoing advances in other areas like computer vision and etc., meant that the solutions that were possible to apply to solve the problems are much bigger, and they were more capable and scalable. So that's kind of, I guess, the biggest change that has happened. But robotics and self-driving is not just machine learning. There's a lot of controls, testing, things like that involved. So it's a gradual thing, and I think it's built up over like a decade or more.
Right, thanks. So the audience, please send in your questions in the chat. In the meantime, I'll have a follow-up question. So when it comes to self-driving, you said now more machine learning came into the equation, I think maybe compared to some years before. So when it comes to, let's say, having a state machine in a robot, right? You do this in this situation, you do that in the other situation. So in this kind of situation, it's difficult to have a actual finite state machine coded, right, with lots of rules. So how does a self-driving car, something as complex as a self-driving car, handle this?
Depending on the application, like the approach, you may have certain rules, like humans have certain rules of how to interact in like an intersection. You may like a roundabout or something, some rules. Sometimes you can encode this. Sometimes if you have enough data and good model training, sometimes the model is able to robustly learn it. So depending on the approach, it might be one or a mix of things that actually make it work. So
right.
You can't have you can't programmatically go through all the examples of what it will encounter. So it has to be adaptable. It has to see the environment, predict the environment, and figure out the right solution.
Right. So this reinforcement learning had like a bigger role to play recently, because earlier it was probably not that effective.
Depending on the approach, yes. Right. I think like with some of these more recent advances, like reinforcement learning has been there for a long time, but now with enough data and enough supervision, you can kind of supervise these models to predict the right action or pick the right action that's appropriate with a very high dimensional state in some sense. Same with AlphaGo and things like that. Yep. Go ahead.
All right. Yeah. Sorry. Thanks. Sorry for interrupting. Yeah, thanks. We have a question from Ravin. So is machine learning effective in localizing robots in future sparse environments like tunnels, mining tunnels, maybe the ocean?
I see. It depends on the features, I guess. So ocean robotics has its own quirky kind of sensors. There's like sonars and things like that. There's very sparse features. Sometimes the solution is not just learning from data. Sometimes there are like traditional algorithmic approaches to SLAM and localization that work well enough that these are not things that you want to machine learn. Sometimes it's more about, imagine like visual SAM in like a complex environment, for example. Then it's hard to kind of feature engineer such kind of complex enough features that work robustly. So then that's the case where you really need to learn from data. If it's mining tunnels and things like that, maybe I don't think most existing robotics approaches would probably use things like Kalman filters and SLAM and things like that versus some more fancier machine learning approach. That doesn't mean that might not work, but you have a very limited data set and you're trying to learn something from sparse data. You may not want to apply like a machine gun to something that requires a knife.
Right, absolutely. Yeah, I hope Ravin is happy with the answer. Any other questions? Or I will ask some of my own questions in the meantime. So when it comes to coming back to self-driving cars now, right? So how far are we from, this is like probably the most famous question every year we ask, how far are we actually from having a self-driving car that actually can take care of itself without human intervention? And what's
So
missing?
there's different kinds of self-driving. So the type of self-driving that I work in is kind of called level 4 self-driving. So you have a map, you know the domain you're interacting in, and you kind of limit yourself to that domain. Even within it, maybe sometimes you may not take like highways, for example, if you feel like the highways is not the kind of operating domain that you can operate in. So there are already systems in cruise, so Waymo, things like that, where driverless operations are possible and have been going on. So in some sense, there are city level deployments that you have. This example already, which was not really possible like 5 years ago, it was hard to even imagine seeing that kind of deployment. That being said, the kind of level 5 systems, the kind of thing that Tesla or Elon Musk is wanting to try, those kinds of solutions are very challenging because you're effectively asking it to do what a human does. No map or very limited map, and still be able to drive safely and effectively. Those kinds of self-driving systems are 10 years out if you're lucky. So because you have the bar to driving is very high, so it's safety critical. So home robots and other things, there are techniques being developed that are, for example, used in self-driving right now that are more easily applied because the safety critical nature is very less, in that you're not driving super fast, you're not gonna cause a severe accident, things like that. The bar for self-driving or some of these safety critical kind of applications, it's the long tail. If you really can't handle like the 0.0001% of the case, it's effectively kind of blocking you from actually deploying.
So currently,
So
would you think we are like at 99.9 something, or?
it depends on your assumptions. If you know the map, sometimes
Right.
it's much easier to predict what other agents will do. So if you don't know the map, the performance of these systems is much lower. So
So
then
for
you're
this
not at the
environment,
99.
so for this environment that you are working in level 4, right? So with the map, given the
Mhm.
map, so is it like how effective that is? So how much of a percentage that you think you can handle the situations while driving?
Depending on the city, like the cities that we deploy in, they're like 99.99 something, because
Right.
most of the time they effectively autonomously operate. Sometimes they know when they're failing. So then you can kind of fall back to getting assistance from a human or something. That depends on your specific setup, but there's still limitations. It's like you can't take this in like heavy rain sometimes, depending on the sensors, or snow and things like that. So it's definitely significantly advanced, but of course there's some places that you will not be able to operate right now because of limitations in sensors, limitations in data, limitations in algorithms and components. It just depends.
Right. All three: data, sensors, and algorithms need some improvement. Right. We have a question from Tarindu. So is having remote drivers motoring level 4 self-driving cars till we reach level 5, is that a viable solution to take care of complex situations faced by level 4?
So level 4 systems can be deployed within, like, let's say you map a city, you train the models to be very performant on that city with enough data. You can confidently deploy it within, like, let's say 25 square mile city or something. But that system will not easily work in any place. There are a lot of assumptions that get built in based on having a map and things like that. So if you want to build a level 5 system, you'll need to build a level 5 system. If the level 5 system has some 0.001% failure, then maybe if the system can understand that it's failing, then you can call, like, get human assistance. If the system doesn't know when to require human assistance, then it's not deployable. If that kind of answers that question.
Yeah.
So it depends. Like, there are level 3 systems now that is a little bit different from level 4, but maybe they apply more broadly in some sense, because like Audi and other companies, they have some of these level 3 systems where they can drive in most highways. And there are the level 3s that you don't have to be paying attention, but sometimes it may encounter some out of domain example, and then it will require the driver to take over. So if it's seeing construction or something, it can detect that it's construction, but it doesn't know how to reroute through cones and things like that. So it'll be like, okay, you need to take over within 2 seconds or 10 seconds or something. So you need something similar but more advanced for a level 5 system to operate in a lot of unmapped or unknown areas, but still be able to request either your human who's occupying the car to take over if it's such type of car, or some remote person to take over.
Right. My last question is more a general machine learning question for you. So in research, we see the typical popular paper coming in many conferences. Usually it has to do with lots of computational power. So like latest developments are coupled with apparently lots of computational resources. So students and researchers not having access to large clusters. So what do you recommend for them to like niche upon, or what kind of contributions can they make with limitations they have?
I think it, like, if you're trying to solve like a really huge kind of generalizable model or something, maybe that's not the right solution unless you have that right compute resources. But there's lots of other things like different architectures, different training techniques, maybe things that allow the model to converge faster or with less data and things like that. They don't necessarily need you to have as much compute. And sometimes for research kind of purposes, you can define the domain or the problem constraints. So if you define the constraints in a way different, like either it's a theoretical proof or something that doesn't really require to extend it to like tens of gigabytes or terabytes of data that require like clusters of GPUs to train, that would be challenging. So yeah, there are enough problems, I think, still that don't require you to kind of really solve, like really apply a lot of compute to it. And I think it's finding the right problem. At least the data and some of these state-of-the-art techniques, they are much more publicly available than they were like 5 years ago even. So you don't have to be in a country, you don't even have to have a self-driving car set up to actually like now solve some of these challenging problems in self-driving or computer vision, but do need to, you may not be able to solve everything as someone working in Sri Lanka without that level of like resources sometimes.
Right. All right, so I think we are 11:01 in Sri Lankan time. I thank Dr. Sachithra Hemachandra a lot, based on behalf of data research and computer science department, University of Moratuwa. And also, I think we also answered all the questions. There's one more thing. Tarindu is sending a link for everyone who's attending the seminar.
That all the participants will their feedback. And thank you, Dr. Thanuja, for helping me with help coordinating the Q&A and for the lovely questions. And thank you, Dr. Sachi, for patience and very meaningful answers. This talk was very fundamentally, you started and gave a very nice, broader and depth picture, very useful, I believe. And truly appreciate your time and effort, and hopefully we'll be in touch with you and get more from you for the data research team, and appreciate it.
Thank you.
Thank you, everyone. Thank you.
Good day.